Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing Unit 10, Lesson number 3 on Basic Polar Calculus. So, up to this point in time, the assumption's been that you had some exposure to polar coordinates and polar curves last year. And this year, we're looking at reviewing that work, which we did in the last two lessons, and now we push it towards the side of calculus. All right? And let's jump right in, because fundamentally, a lot of calculus at the beginning concentrates on a single thing, right? It concentrates on calculating the slope of a curve. So I want you to keep in mind that even though we've got r as a function of theta, right, ultimately speaking, just as we had in parametrics, right, that's going to trace out some kind of a curve. And at a particular theta, whatever it is, there's a tangent line. And that tangent line, that was supposed to be a tangent line. We all know how bad I am at drawing those. That tangent line has a slope, literally a y versus x slope, dy dx. So no matter what the variables are, r, theta, x, t, y, t, we're still graphing in the xy plane, and we can still ask at a particular moment in time or at a particular angle, how fast is the y-coordinate changing compared to the x-coordinate. All right, the key to doing this, and this is really kind of cool, is treating polar as a subset of parametric. That's actually where we ended last time. Now remember, from parametric, we had a very simple relationship, right? We knew that dy dx would be dy dt divided by dx dt. And this worked because both x and y were functions of a single third variable, f of t, g of t. Well, we can do exactly the same thing in polar. It's going to get awfully ugly, okay, and the numbers aren't going to be pretty at all. But just bear with me, right? What we can say, obviously, is that x is equal to r cosine theta. But because our friend here, r, is a function of theta, we can just put that function of theta in. So x is actually 2 times sine of 3 theta times cosine of theta, and y, which is r sine theta, right, will be 2 times sine of 3 theta times sine theta. And really what we have at this point is exactly the same situation here. The only difference is what we're calling the parameter. We're calling it theta now instead of t. We think of theta now more as an angle versus t as time, but the mechanics still work out exactly the same. Dy dx is still ultimately going to be dy d theta divided by dx d theta. Remember, this is just an expression, really, if nothing else, of the chain rule or the chain law. So let's do it. It's a little bit messy. Students vary in how they like to do this. A lot of them will sort of take those two derivatives separately, then substitute them in. Some people will just immediately start applying. One thing to be careful about, almost always students will write down the x-coordinate first and the y-coordinate second, and yet in the fraction it's dy d theta divided by dx d theta. Just watch how many times you make a mistake on that, seriously. But I think I'm going to actually figure out dy d theta first, and separately, I'll just do it here. To figure out the derivative of this, I'm going to have to use the product rule, right? So I'm going to get 2 times the cosine of 3 theta times 3 times the sine of theta, right? That's the first part of the product rule, plus then the derivative of sine theta, which would be cosine theta times 2 sine 3 theta. Okay, that's my dy d theta. If you like, you can get ready to immediately do the calculation by sort of like now doing the division. So dx d theta, very similar pattern, right? We're going to get 2 times the cosine of 3 theta, product rule again, times 3 times cosine theta, right? That 3 is coming from the chain rule on the sine 3 theta, just to make sure you realize that. Plus, now I'll take the derivative of cosine, and I'll get negative sine theta times 2 times the sine of 3 theta. Woo! That is messy. And almost all of these are messy, quite frankly, because they're all going to involve a product rule. They're all going to involve a product rule. X is always going to be the product of r and cosine theta. Y will always be the product of r and sine theta. Sometimes the product rule will be easier. Sometimes it'll be harder. This is, I think, actually a relatively easy one. Now the question, how much do you want to simplify this before you ultimately substitute pi over 6 in? That's really kind of up to you. I made the numbers actually work out relatively nice here, because if we put pi over 6 in and we multiply it by 3, we get pi over 2. So you want to do that immediately, times 3 times the sine of pi over 6 plus the cosine of pi over 6 times 2 times, oh my gosh, am I going to have enough room? Oh, I did it. Just barely. Maybe try to write a little bit smaller next time. 2 times the cosine of pi over 2 times 3 times the cosine of pi over 6. I'm going to just incorporate this negative right here, right now, minus the sine of pi over 6 times 2 times the sine of pi over 2. Now, what people who've done a lot of math will tell you is that, especially when you're dealing with an ugly expression like this, it's actually very helpful if you recognize that certain things are 0, if certain things are 0. So for instance, the cosine of pi over 2 is 0, so it's like the rest of this term is actually completely irrelevant. And the same thing here, the cosine of pi over 2 is 0, so this is all gone. The rest of it, let's actually also do in red. The cosine of pi over 6 is root 3 over 2. Then obviously we have times 2 times the sine of 1/2, which is 1. Right down here, we don't want to lose that negative sign. That came along for a ride. The sine of pi over 6 is 1/2 times 2 times the sine of pi over 2, which is again 1. In the numerator, these two will cancel. In the denominator, these two will cancel. And ultimately speaking, all we'll have left is a negative root 3. There we go, the slope of the tangent line. That's pretty amazing, isn't it? The slope of the tangent line when theta is pi over 6. All right, write that down. There was a lot of development there, and then I'm going to scrub out the text, okay? Here it goes. Yeah, we have a part B to this problem. Let's read it over. Create the Cartesian equation, right? That's an equation in x comma y for the tangent line at theta equals pi over 6, then convert it to its equivalent polar form. Finally, graph both the polar function above and your tangent line using the window. All right, let's go Cartesian. I tell my students every time they see write the equation of a tangent line, especially if it specifies in Cartesian form, just immediately write this down, right? Now, one of the nice things is we need to figure out y1, m, and x1, and we have one of them already. Not the one we typically have at this point. Which one do we have? Yeah, we have m. And that's what we figured out in the last problem. That was that negative square root of 3, which is kind of nice, right? That's always and forever will be dy dx. The question is, where do we get x1 and y1? Pause the video for a second and think about that, because anytime you hit a roadblock in math, you really want to try to overcome that roadblock on your own. So pause the video for a second. All right, let's go through it. It's very simple. You know, all x coordinates in this problem will be given by r times cosine theta, all of them, right? We actually have a complete formula for that. That's 2 times the sine of 3 theta times the cosine theta, right? And what I really need is I need x at pi over 6, right? So that's going to be 2 times the sine of pi over 2, I just did that multiplication immediately, times the cosine of pi over 6. Let's see, that's equal to 1, and I've got my 2, and the cosine of pi over 6 is root 3 over 2. So my x1 is root 3 as well. I bet you can figure out why now, right? Why don't you go ahead and pause the video and do that if you haven't already. All right, let's go through it. Same deal, same song. Second verse, as I like to say, r sine theta for y. So that's going to be 2 times the sine of 3 theta times the sine of theta. All right, let's now figure out what the y value is when theta is pi over 6. That's going to be 2 times the sine of pi over 2 times the sine of pi over 6. That's equal to 1. That's equal to 1/2. And all of that's 1. Woo! So we have it. Y minus 1 is equal to the square root of 3 times x minus root 3. There is our Cartesian equation. But we have a second thing that we have to do, besides the graphing. That's the third thing. We need to convert that to polar. And one really good reason for that is I want to look at this polar curve and I want to look at its tangent line. I want to see them both on my equation, on my calculator. So now we have to go back to a skill we've already learned, which is how to convert an equation which is in Cartesian form, xy, right? How to take an equation in xy form and convert it into an equation in our theta form. Now, normally what we would do is we'd just immediately say that y is r sine theta and x is r cosine theta, and that would work. I find it's a little bit easier in this particular problem if we distribute. That's what happens when I try to talk and do math at the same time. If I distribute that square root of 3, one thing that's nice is root 3 times root 3 becomes 3. Oh, that was a negative root 3. That's a negative. I apologize. Although that then becomes a positive 3, which is kind of nice. And then y ultimately is negative root 3 x plus 4. All right, it's going to be easier to manipulate this one, right? Because now what we can do is we can say that y is r sine theta, x is r cos theta, and 4 is the number 4. All right, we're going to pull this over to the other side, so we're going to have r times sine theta plus root 3 r cosine theta equals 4. We're now going to factor out that variable that we're solving for. Just like so. And finally, we'll solve for it to get a not so attractive polar equation of a line. All right, there it is. Our polar equation. Polar equation, Cartesian equation. Of course, you could also have left your Cartesian equation in that like y equals mx plus b form. Now, the beauty of having that polar equation is now what we're going to do is we're going to open up the TI-84+. So let's do that now. All right, now that we've got our calculator open, we're going to make sure we're in polar mode. And we are. So let's go into y equals, or now really r equals. Let's clear out any equations we might have in there, probably from the previous lesson. All right, now what we're going to do is we're going to put in, for r1, our original function. So we're going to put in 2 times the sine of 3 theta. Okay, make sure it looks good. Now, for r2, we're going to put in the more complicated tangent line equation. So that's going to be 4 divided by, make sure to get those parentheses in there, sine theta plus square root of 3. Watch out, make sure that cosine theta doesn't end up under the square root, times cosine theta. Okay, close the parentheses on the denominator. Really make sure that that tangent line equation looks right. You know, that can be easily entered incorrectly, and then it's going to look totally wrong. All right, so we really take a look at it. Looks good. The window is told to us, so let's go into that window. Okay, theta min is 0. Theta max, 2 pi. Probably what you have set in there already, but you never know. X min, negative 3. X max, 3. Y min, negative 3. Y max, 3. Now, at the end of the day, we should see some kind of polar curve. Maybe we don't even know what kind it is, and then we should see a tangent line. So let's do it. Graph. I absolutely love polar graphs. And then their tangent lines are just so cool looking too. Right? Isn't that a nice graph? Love it. And it's a great check too. You know, if you have your calculator available and you're asked to graph or to create the equation of a tangent line in polar, which is pretty challenging. You know, it takes some time, you know, from the get-go. It's a wonderful, wonderful way to see if you've got the right equation. So I'm going to clear out the text, copy down anything you might need to. All right, here it goes. All right. Everything after this is really just work with that fundamental procedure. The work can be messy and not particularly nice answers. Sometimes the slopes can be undefined, maybe if we have a vertical tangent line there. So there's really nothing new on the problems on the back side of this sheet or in the video. So what I'd like you to do is take a shot. Try to do letter A. We're going to find dy dx for a simple polar curve, r equals theta squared, when theta equals pi over 2. So try to find dy dx for that, and then I'm going to just walk through it. Okay? Pause the video, maybe even take up to about 10 minutes of time. All right, let's go through it. It's actually very, very standard. It all rests on this fundamental principle. Dy dx is going to be dy d theta divided by dx d theta. In order to have this, we need x as a function of theta. X is r times cosine theta, and in this case, r is theta squared, so x is theta squared cosine theta. Y, on the other hand, is r times sine theta, which would be theta squared times sine theta. Again, my one caution is this is almost always the way students will write it down, but then the thing that's in the numerator is dy d theta, that quantity in the denominator is dx d theta. So as tricky as it may be, you gotta start with this one. Anyway, it's product rule again, right? The derivative of theta squared will be 2 theta times the sine of theta, plus then theta squared times the cosine of theta, divided by, whoops, that's wrong. Sorry about that. Now I have to take dx d theta, so that's going to again be 2 theta times now cosine theta, right? Plus theta squared times negative sine theta. Notice we're always going to introduce this, so for some students, if they do enough of these problems, a lot of students will simply start to incorporate that subtraction almost immediately, because it will always happen. You'll always get a subtraction right there. Now, I want to really caution you. It would be so simple to look at an expression like this and start to do things that are not permissible algebraically, like say things like, oh, cancel out the 2 theta and the 2 theta, cancel out the theta squared and the theta squared. It's not correct, so don't do that kind of simplification unless you're absolutely certain it's true. Let's substitute theta equals pi over 2 into our expression. Again, going to be kind of ugly, but it is what it is. That's 2 times pi over 2 times the sine of pi over 2 plus, pi over 2, make that look a little more like a plus, pi over 2 squared times the cosine of pi over 2. Unlike parametric derivatives, the numerator and the denominator in these are almost identical, so a lot of times you can kind of take advantage of that if you know your trig. So again, I would highly advise in a trig scenario to think about things that are 0. For instance, the cosine of pi over 2 is 0, so those two terms are out. The sine of pi over 2, that's a nice number, that's equal to 1, so that's not too ugly. I'll just finish it in red. Here the 2 and the pi would cancel, giving me a pi. Here I don't have to worry about it, that went to 0. In the denominator that went to 0, that's 1, so I'm going to get negative pi squared over 4. And that will simplify to negative 4 divided by pi. All right. Not too bad. Again, not the prettiest answer, but it's not too bad. I'm going to clear out the text, so take a look. Think about the procedure. It's pretty mechanical, but important. You got it? Okay, I'm clearing this out. Let's do another one, or have you do another one. So again, here we've got r equals sine theta, a simple enough polar curve. I would like to know what the slope is when theta equals 3 pi over 4, so work on it. Okay, take up to 10 minutes. All right, let's go through it. It is what it is. Oh, I'm still in red. dy dx, it's kind of snappy this morning, though. Is dy d theta Yeah, there's a real term. Divided by dx d theta. All right, maybe I'll go back to blue. I don't know. I think red should just be reserved for really drawing your eyes to things. Okay, x is r cosine theta, which is going to be sine theta cos theta. If we wanted to get cute, we could probably use a trig identity there, but I don't feel like being cute right now. Y is r sine theta, which will be sine theta times sine theta. You could certainly express that as sine squared theta. I don't see a huge advantage there, but you could. Then you'd be using the chain rule instead of the product rule. Either way, dy dx is going to be dy d theta, so I need to take the derivative of this. That's going to be cosine theta sine theta plus cosine theta sine theta. Right? Again, just the product rule. Divided now by the derivative of this, that's going to be cosine theta minus, right, because I take the derivative of that, sine theta. And I want that at theta equals 3 pi over 4. It's going to be a little bit more of an ugly answer. Cosine 3 pi over 4, sine 3 pi over 4, my plus, I don't know why I keep putting a minus there, cosine 3 pi over 4, sine 3 pi over 4, divided by cosine of, actually, you know what, cosine of 3 pi over 4, now I'm going to do it, squared minus sine of 3 pi over 4 squared. All right, well, let's see. Cosine of 3 pi over 4 is negative root 2 over 2. Sine is positive root 2 over 2. That's really all we need in this entire problem. Negative root 2 over 2, positive root 2 over 2. So the top actually would be negative 1/2 minus 1/2. If you think about it, right? Negative root 2 over 2. Sorry about that. I thought, here I'm doing this in my head, and it may not be the most obvious thing, right? It would be negative 2 over 4, which would be negative 1/2. Here's the beautiful thing, though. Down in the denominator, we're going to make our lives very simple very soon. We'll have 1/2 minus 1/2. So we get negative 1 over 0. So of course what that means is that the slope is undefined or does not exist. All right, probably means we have a vertical tangent line. All right. So let's clear this out. It's gone. Now, one of the weird things I've always found about calculus is that calculus textbooks tend to be just littered with formulas. Formula. And really, all of these formulas, you really don't want students to memorize. There's some basic things like the product rule, the quotient rule, things like that. But if you open up every calculus textbook, you'll actually find a formula that says if r is equal to f of theta, r is equal to f of theta, then dy dx can be calculated by using this formula. Now, lots of students will just memorize the formula. What I want you to do in this problem is come up with the general formula. So pause the video and do exactly what we just did, but use f of theta instead of a specific function. Take about 5 minutes. That should be all you need. All right, let's do it. Let's see why you can write a textbook. Right, what do we have? We have x equals r cosine theta, which is going to be f of theta cosine theta. Y is going to be r sine theta, which is f of theta times sine theta. So dy dx is going to be dy d theta divided by dx d theta. Dy d theta would be f prime of theta times sine theta plus f of theta times cosine theta. Right? That's the derivative of the y function. And the derivative of the x function will be f prime of theta times cosine of theta minus f of theta times sine of theta. Can you imagine memorizing that formula? Like the amount of work it takes to memorize that formula compared to the amount of work it just takes to understand this very simple idea that polar is a subset of parametric, and when you've got x as a function of a third variable and y as a function of a third variable, then all you ever have to do to find dy dx is do dy d theta divided by dx d theta, dy dt divided by dx dt, what have you. I don't think we need to memorize that formula. All right, clearing it out though. Bye-bye formula. All right, so that was some basic polar calculus. We're going to look at one other piece of polar calculus in the next lesson, and then we're going to leave the rest of it to the college professors and to the BC calculus teachers. For now, let me just sign off by saying this has been another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.